Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today we're looking at day 11 of the Advent of Code challenge. Let's take a look at this puzzle. Today's puzzle is called Plutonian Pebbles. So, as with yesterday, I'm going to read through the puzzle. There'll be timestamps in the description that should highlight on the video too, so feel free to skip ahead if you don't want to hear the puzzle. Otherwise, I'll read it out. Plutonian Pebbles. The ancient civilization on Pluto was known for its ability to manipulate space-time. And while the historians explore their infinite corridors, you've noticed a strange set of physics-defying stones. At first glance, they seem like normal stones. They're arranged in a perfectly straight line, and each stone has a number engraved on it. The strange part is that every time you blink, the stones change. Sometimes the number engraved on a stone changes. Other times, a stone might split in two, causing all the other stones to shift over a bit to make room in their perfectly straight line. As you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones each simultaneously change according to the first applicable rule in this list. If the stone is engraved with the number 0, it is replaced by a stone engraved with the number 1. If the stone is engraved with a number that has an even number of digits, it is replaced by 2 stones. The left half of the digits are engraved on the new left stone, and the right half of the digits are engraved on the new right stone. The new numbers don't keep extra leading zeros. 1,000 would become stones 10 and 0. If none of the other rules apply, the stone is replaced by a new stone. The old stone's number multiplied by 2024 is engraved on the new stone. No matter how the stones change, their order is preserved and they stay on their perfectly straight line. How will the stones evolve if you keep blinking at them? You take a note of the number engraved on each stone in the line, your puzzle input. If you have an arrangement of 5 stones engraved with the numbers 0, 1, 10, 99, 999, and you blink once, the stones transform as follows. The first stone 0 becomes a stone marked 1. The second stone 1 is multiplied by 2024 to become 2024. The third stone 10 is split into a stone marked 1 followed by a stone marked 0. The fourth stone, 99, is split into 2 stones marked 9. The fifth stone, 999, is replaced by a stone marked a big number, over 2 million. So after blinking once, your 5 stones will become an arrangement of 7 stones engraved with the numbers, these numbers. Here is a longer example. Initial arrangement after 1 blink, and it goes through the sequence showing how they evolve over time. In this example, after blinking 6 times, you would have 22 stones. After blinking 25 times, you would have 55,312 stones. Consider the arrangement of the stones in front of you. How many stones will you have after blinking 25 times? I immediately love this puzzle. There's a game, I guess it's called, a simulation called Conway's Game of Life. You get very complex behavior from a very few simple rules, which is what I thought of immediately when reading this puzzle because of these rules. Having understood it further, I don't think it's that similar. I don't think it's really relevant, but it did give me that initial rush of excitement about about coding something similar to Game of Life for Advent of Code. Still, it seems really interesting. So my first thought is we should be able to calculate each stone separately. So because they retain their order and they don't depend on one another, it should be possible to take the number 125 and run the simulation on it, and then take the number 17 and run the simulation on it and stick those two together. Or rather just add the number of stones that they create. More than that though, we can keep a cache of the calculation. So I haven't thought this through completely, but I think we could take the number 17, simulate it to 25,000 times, that's 25 times, and just store the number that it produces in the end. And then if we see 17 elsewhere, then we can just use that number again. Now that only works if 17 is likely to appear again. Judging from this test example, we're not saving ourselves much work by doing that cache. Instead, what might be better is to cache the result of one step of the simulation. That will just mean that we do a hash map lookup instead of an if and then a multiply. So again, I don't think that's saving us that much effort. I'm going to try just running the solution one number at a time until I get an answer. I imagine there's a way to make this much faster, a way to optimize it. I can't think of it just from reading through the puzzle. So I'm going to attempt a solution and see what problems I run into. So I'm going to set up the project and I'll cut to when the project is ready. Okay, so the project is ready. Just hello world in the main file and a test.txt with the stones that were given by the puzzle. So I'm going to sprint through the early stages. I don't think there's a lot of interesting stuff here. I'm going to create a test that checks the test that it gives us, the example small text. Just like that. And then with that test in place, cannot find function for in the scope, that's fine. With that test in place, I'm going to create a structure to read the puzzle into. I don't actually think it needs to be much of a structure. It's actually just a vector of numbers. But it gives me the opportunity to store a cache or anything if I do want to do that. So I am going to go ahead and create a structure for it. So I'm going to call the structure Pluto Stones, which will contain the stones, which is a vec of U32, I think. Is that okay? That should be fine, although insertion into a vector is a bit annoying. But that's fine. We'll deal with that when we get to it. Okay. I guess we don't actually need to store it as a vector. We can store it as a hash set. But a hash set will deduplicate it, so that's not great. Okay, never mind. Let's implement for string on this from string. String for Pluto Stones. And just like yesterday, I think that the error type will just be a parse-in error. So I'm just going to directly set that instead of creating a new enum for it. Then I'll do the from string function, rename s to puzzle, and return an OK Pluto Stones with an empty vector. Okay, everything should compile there. So let's go ahead and actually parse the puzzle. So the puzzle will be puzzle.split by whitespace. For each result, we're going to map that string to the parsed version. And then we're going to collect that together into a vector. That means I can remove this empty vector, and that should just work. Now, I do actually want to check this because I don't think I've ever done it. Rust map return if error. You can use try for each. Oh yeah, so I can store the results and then question mark on the output. Yeah, it looks like it. So if I don't do this and I instead move the question mark to the end, parse needs to be given the type it's going into. which is U32. And then we can't collect it. Let stones result. Now we can remove this question mark. We should get our type inference done on it, which is unknown. Interesting. Okay. Equals stones result. Yeah, it doesn't know. Okay, so we're going to collect it then into a result of vector of U32 and a type we don't care about. Might have meant to add the type parameters here. I did. That actually seems okay. So now can I just directly... Yeah, it looks like I can get stones from it. So this is different from how I parsed the puzzle in previous days. A lot of the time, if it fails to parse, I just filter it out. I just ignore it. This time, I'm being more strict. I'm saying if anything fails to parse as an integer, we're going to fail to parse overall. And then I should have to handle that in the main function. Which is strictly speaking more correct. It's less required for advent of code, but it's something that I wanted to learn how to do anyway. And this actually did make it quite simple. Just needed some type inferences to make it all work. Okay, so we've got the puzzle parsed. Next step is to start implementing the solution. Pluto stones. Function part A, which takes a reference to self and returns a usize. And first it will return 0. Okay, now I can change my test. This will now say let stones is Pluto stones parse, from string puzzle. We'll unwrap that. And then it will be stones.part A. And then at this point we can run cargo test and see the failure because part A just directly returns 0. Okay, so we're now at the point where we can start implementing the puzzle. Implementing the solution to the puzzle. Now for each one of these stones, I want to calculate independently what it becomes. So for that, I'm going to create another function. It doesn't need to be, it doesn't take any part of Pluto stones at the moment. So I'm going to define it as stones after 25. Doesn't take self, it will take the initial stone. And the initial stone will be a U32. Okay, so in fact, we can make this recursive. Do I want to make it recursive is the question. It would be simpler, but I don't think there's any point in doing it. Okay, so let's do it like this. One interesting thing is that for this solution, we don't need to keep the order. We can just, anytime we split a stone, we can replace the value and append a second value to the end of the vector. They don't affect each other, so that's fine to do. The issue in that case is that the puzzle specifies that they stay, their order is preserved. So that's interesting. If we write it like this, part 2 might make things more difficult for us. But I think because I don't know what part 2 is yet, I'm not going to try and change my solution to anticipate it. I'm going to go ahead and append new values to the end of the vector. Right, so let mute stones is a new vector. We're going to iterate 25 times. For each time, we are going to I'm just going to take create a closure here, which will take a stone and return the result of the rules. So it will be another stone or an option. So I'm going to code this up by just saying 0 and none. So I'm going to say left, right. Actually, I can do for stone in stones. Let left, right, opt equals apply rule to stone. I can reference this, so I can say get mute. I can iter mute. Here we go. Although that's a problem because then I can't append to the vector while I'm iterating over it. Yeah. So what I might do is just rebuild the vector every time. Let mute next stones is vector of nothing. For stones, the stone in stones, let left, right, opt equals apply rule stone. We will push onto next stones the new left value, and if let sum right equals right opt, then we will push right. And in this case, I am actually keeping the order intact. So my fear about that was for nothing. So stones will become next stones. I think we may need to make that mutable for it to work, which is a bit of a shame, but that's fine. And then once we're done, we're going to return stones.length. Okay, that's all fine so far. We do need to encode the rules that the game has given us yet, but let's make use of this function. So it will be self.stones.map. I suppose we need to iter, so iter.map, where each initial stone returns Pluto stones, stones after 25 stone, and then we will sum. I can take a reference to the stone here. There we go. That dereferences it in the closure. Okay, so the only thing left to do is to implement the rules. Let's do that. So the rules are, if it's a 0, it becomes 1. I can match on stone. If it's 0, then return 1 and none. If it's... sorry, I can just read the rules here. If it has an even number of digits, then it's replaced by 2 stones. Okay. Stone.length. This is a bit weird to use a match statement for. I think I would rather use an if let or an if. If stone is 0, return 0, none. That's wrong. It should be 1. Else, if stone dot to string. Actually, I can do a let stone str equals stone dot to string. Is that not allowed? Oh, it doesn't know what stone is. Stone is a U32. Is that okay? Yeah. So if it is an even number of digits, it's replaced by 2 stones. So we can mod 2 equals 0 to check whether it's an even number. And if it is, then we will return. We can divide this up into separate statements. So there's the left stone, which is the stone string dot substring, I think. Do I need to substring it? Or can I index into it? Rust string take n characters. How do I get the last n characters? Fine. Can I just index it? Car indices nth back. Okay. Nth. No, that didn't work. Oh, car indices. Car indices dot nth. And that will be the nth. Nth returns a single value, so I think I want the take. And we're going to take the stone.str stone_str.length over 2. And then we're going to collect that to a string. And then we're going to parse it. Now that, I believe, is guaranteed to work because I got it from numbers. So I'm going to just directly expect a message. Could not parse digits. Could not parse string. In this case, I'll format it. In previous days, I have thought that there's no possible way it could get to an error message, but gave it an informative error message anyway. And thankfully, that gave me more information and helped me solve the problem. I would probably have to divide this into multiple lines to be able to do that, though. So I am going to do that. So left string is stone_str car indices and collect into string. Might not even need the type inference if we define that left string is a string. That's a string. I do prefer specifying the type of a variable rather than using the turbofish. String cannot be built from iterator over usize and car. And their positions. Oh, okay. I don't want the positions. I'm going to take and I'm going to map. I think it'll be an index and the character. And I want to give the character back. Yeah. I can check because it said that index was a usize and C was a character that I got that right. Okay, so again, I'll do this for the right. I might make this n cars and then store this once just to make it slightly more readable. So we're going to take n cars and we're going to n back n cars. Then we're going to parse the left string. Could not format string, left string. Do the same for the right. Why is this upset? Not enough brackets. Try that. Still not happy. Wants a reference. That's happy. Okay. No method name collect found for option character. Unwrap? No. So nth back returns an option. So I want to actually unwrap that. Or expect it. Not enough characters in string. That expect should then give me usize car is not an iterator. Is it because it's not giving me the... What type do you take? C. What is C? C is unknown. I'm really struggling with this iterator, so let's nth back. Maybe I can write this in a different way rather than solving it completely. Let's do let mute car equals stone string dot cars. Oh yeah, I can do that here as well. Can I do car iter dot take? Assuming that doesn't consume it. Left string is car iter dot take n cars, and then hopefully I can do the same with the right. I tried to do this with another puzzle recently, and I couldn't mutate the iterator like that, but it seems to be happy. So I'm going to go ahead and collect into a string, and give it a string type, give it a string type, and then delete all of this. And that should be happier, I think. Type annotations needed. Type must be known at this point. Consider giving left an explicit type. Well, this needs to be right, and it needs to be right string. And then it knows its reference because I can return left and OK right. Actually, it's some right. Okay, so that's the string split rules. That should be okay. Character iterator does not need to be mutable. I really thought it did. Okay, I can't. Yeah, that's what I thought. Okay. So let's try again. Left string is, well, I can just replace this with stone string.cars take and stone string.cars skip and cars.take and cars, which is pretty much equivalent. So this should actually be right string and use of expect followed by a function call. I don't understand. Try unwrap or else. Why is that better? That's the same thing but with worse syntax. Okay, I don't understand that recommendation, but if you do have a good reason to do that instead, please write it in the comments. Because yeah, I really don't get why it recommended doing that. And then, okay, so that's an even number of digits, fine. If none of the other rules apply, it's replaced by a new stone, which is multiplied by 24. Okay, so at this point, we can just write stone times 2024, none. That's it, that's our 3 rules. We should even be able to just cargo test this, and it failed. Okay, because it attempted to multiply with overflow. It appears that U32 is not big enough. Let's try again with the U64. Still failed, and I got much too large of a number. Okay, so Let's print this out after one step and see what it says. So underscore in 0 to 1. Then we are going to print line stones. Let's give that a go. What did we get? A lot more prints than I expected. Because there's multiple entries in test text. Right. So 1 becomes 2024. That's... Oh, okay. I think I want this. No. The initial arrangement is 125.17 for this one. So I'm actually going to take that. And it says 253,017, correct. Let's go to 2. Oh, it's a different example now. I should have a different result. I may have done it right the first time and just tested against the wrong example. And yeah, that is right. That worked pretty quickly. I do have an odd solution here in that I'm splitting it into individual stones and then for each stone calculating the entire length of the array, which could be enormous. I'm sure there's an easier way and a more optimal way to do this. But let's try it on the full puzzle input and see what we get. I am fully expecting at this point to try it for real and to get a stack overflow from growing a vector too large, but we'll find out. Let puzzle is include string / puzzle input.text. Let stones equals Pluto stones part A. No, we're parsing it. Parse from string on puzzle dot expect could not parse puzzle input. And then we're going to print line the result. Stones dot part A. Let's give that a try. Cargo run. Ooh, left our print statements in. But it ran in fairly quick time, so that should be fine. Let's take the print lines out, the debug print line. Run it again, we should get the same result, obviously. And then we're going to grab that part A and plug it into the answer box. Submit. Is it right? It is right. So we're going on to part 2. That is a very short update. Okay, so part 2. The historians sure are taking a long time. To be fair, the infinite corridors are very large. How many stones would you have after blinking a total of 75 times? I am worried that we are going to stack overflow here. I am very much worried. So let's run it once. We'll run it once and see how much my laptop struggles. And when it inevitably struggles to finish, I'll update it and start trying to split the vector up and merging it together, that kind of a thing. Okay, so here is our initial stone, and we're actually going to take the number of iterations as a U size, probably a U size. Okay, so stones after iterations. It will be called the iterations will replace 25. Where is it? Here it is. Ooh, iterations. That's better. Now our function call should actually be function call after iterations, and we're going to give it 25. And then our part A solution will be, sorry, part B solution will be 75. Now we didn't even get an updated example, so I'm not going to write a new test. I am just going to run it and see it horribly fail. Let's take this to part B, and that's part B. Cargo run, and it is thinking for a long time. I'll keep letting this run while I start trying to optimize it. Now, my first thought to try and optimize it is to split the vector up automatically into smaller chunks and then use recursive function calls. Now, I could recurse down to one level, as in each stone in the vector gets its own recursive function call. That would work just fine. And I don't know if it's worth doing that. There'll be a lot of copying data around, but it might be the right way to do it. I think it's probably not the right way. So instead, what I'm going to do is split it into sizes of 10. I'll take this out to a separate function. It doesn't need to be defined inline. Let's do a apply rule, which will take a stone, which is a U64, and it will return a tuple of another stone and an option of a stone. Now we're going to take apply rule, just grab the whole lot and copy it in here. Okay, so that is our logic. Next, I will delete that, and instead of apply rule, it will be Pluto stones apply rule. Stones apply rule. And at this point, I'm going to say, thing is, it's still calculating, and I struggle to believe that it's not coming across the same number again, which leads me back to this idea about caching. So let's stop this. It's not finishing in any reasonable time. I need to think about this for a moment. My first idea at the start was to cache the result of what happens to a stone. But I do think that it's pretty quick to calculate what happens to a stone. The worst part is turning it into a string, taking half the digits, and then turning it back again into two different numbers. So that is a problem, but I think the caching won't help too much with that. I think the issue is more about finding the optimal way of going in 75 iterations into a step. This might be an entirely different solution. I'm now thinking that our cache might look something like, for a given number, after n iterations, we get an answer of such a thing. Okay? So The point of doing that is that n iterations returns x as a result. So now, whenever I'm going through the algorithm, if I see that I have 25 as a stone, and I have n iterations remaining, I can skip that. I can skip those iterations. I can go directly to x. I can skip all of that intermediate calculation. Now that's useful if there's exactly that number of iterations left. So is there something I can do where I can skip a number of iterations that's not equal to the remaining number of iterations to do? Even then, though, it might help a lot for 75 because it is a multiple of 25. So if I calculate, if I build it into my cache that this number has 1, this number after 1 iteration gives me 2 answers. That's really not useful. So maybe I can do that it caches every 5 iterations, and then it can skip 5 iterations. That doesn't really work. I feel like there's something there. There's something with the cache and the number of iterations that it has left to do in order to give me a result. I could even do that it stores a vector. So if the cache stores the vector of stones after that many iterations, then I can continue simulation having skipped a bunch of iterations. But it's still going to give me an enormous array. Okay, I am not sure if this will work, but I'm going to attempt it just to see what answer I can get. So I'm going to run it so that it'll calculate 5 iterations. After 5 iterations, it will save all of the results that it's got so far. So if it started with 25, then it will store the result after that. Then when there's 5 iterations left, it can look up what the answer is. By looking up what the answer is, it can more quickly get to 10 iterations result. And then when it's 10 iterations from the end, it can skip that. Then it can do the same for 15. And then that might work. It might even be better to just store every iteration. But let's play with doing 5 iterations. I'll see how it goes. So this will be a U64 and a U32 probably. It doesn't really matter. As a key, and the result will be a U30 or a U size. It'll be a U size. Okay. That's our cache. We need to import it. We need to create a new one. Cache is a hash map new. Now, part A needs to be a mut self. Part B needs to be a mut self. And a stones after iterations will take a mut self. Okay. Now we're not going to change the stones array that was originally input. What we are going to change is the cache. So I know that for an initial stone, which is saved by stones after iterations, and after a number of iterations, stones is saved here. So now I can do a cache save. Cache save if multiple of 5 iterations, which could just be 1. We'll see. 5 seems like a good answer because it won't create an enormous hash map with all values. Okay, so for the cache save, we're going to go through... actually, we just literally self.cache.inserts, and our tuple is the initial value. Our number of iterations is our index. And our result is stones.length. But we want index plus 1. So it's 0, 1, 2, 3, 4. So on 4, we want to save the number of iterations. So it'll actually be index plus 1. And then our check will be if index mod by 5 is equal to 4, meaning so 0, 1, 2, 3, 4 is the 4 is the 5th iteration. So I'm going to check if dividing by 5 has a remainder of 4. If it does, that means it is 1 below a multiple of 5, which is what we're looking for. You can convert a usize to a U32. Index is a usize, so I'm just going to save it as a usize. U32 I just pulled out of the air anyway. And then we need and mut self. Wait, do I need to do that? No, I don't. I just change this double colon to a dot. Oh, it'd be self dot. Self dot. That's better. We can't do that because we're already borrowing self. It is honestly probably easier to just clone it. Which is a bit of a shame, but what can you do? Self.stones.clone. Now we're just going to iterate over stones. Then that's okay. This is the Rust borrow promise. You can either borrow it multiple times read-only or one time write-only. You can't borrow it at the same time read and write. So we were borrowing it in read-only and then trying to borrow it in write-only at the same time. And it said, no, you're not allowed to do that. It's pretty easy to get around in this case, but if you've heard of Rust fighting the borrow checker, that's one instance of it. Okay, let's check on this. We need to declare this as mutable now, and we need to declare this as mutable now. Purely because we have the cache. Now I could store the cache, I could build the cache within stones after iterations, but doing it this way means I can reuse the cache across parts of the question, which is quite nice. Okay, with that, let's take a look. So, for stone in stones, check if stone is cached with n iterations remaining. If iterations minus index mod 5 is 0, is that it? I'm not sure it is. Let mut accumulator is 0. Plus stones.length. Okay, so let's think. So, if we're doing 25 iterations, then on iteration number 20, there will be 5 iterations remaining. So 25 minus 20 is 5. Mod 5 is 0, which means it should have an entry. So at this point, we should be able to say well, actually we can just do let iter remaining is iterations minus iter. Let's see that. Okay, so if let sum x is equal to self.cache.get, which will be our current stone and our iter remaining. Yes. Iter remaining is unknown, so I can call that a usize. Oh no, that's okay. Iterations minus index, not iter. There we go. Then accumulator plus equals x, continue. That should be the caching logic done. So if I cargo test this, I should get the same result. I do. So I'm going to cargo run it and see if it does anything to help us. It's not looking like it. It's still taking quite a long time. What I'm going to do is remove the requirement that it's every 5. Let's just go with that. That gives me a different result. That's not right. Cargo test it works. Cargo run is different. It's different both times. Something's wrong with the caching logic. It's not even speeding us up that much. Is it the index plus 1? It's had 1 iteration, so store that, and then it's stones.length. That should be right. If let sum is self.cache.get stone and iter remaining, then we add on that key and continue, which doesn't push it onto next stones. Otherwise, we continue applying the rule to it. Is there some pattern here that I'm not seeing? We do know that 0 and 1 are very common. Let's try caching 0 and 1. This is odd, and I have no idea if it'll help, but it's slowed down part 1 a lot. Yeah, I guess it's running 75 iterations, even starting from 0. Very, very expensive. Okay, so I think that puts paid to the cache idea. I think the video has gone on long enough. I think I've attempted to do this for around about an hour. If I thought I was within sight of the finish, then I would carry on. Fortunately, I don't think I'm going the right way with this. I need some time to mull it over in my head. So I will be back tomorrow to continue day 11 and see if I can come up with a better way of solving this problem. Until then, thanks for watching, and I'll see you tomorrow.